Hello and welcome my dear students. In this video, we will discuss about the applied thermodynamics. In applied thermodynamics, we learn about the thermodynamic cycle. Okay, let us start the thermodynamic cycle. We broadly classified thermodynamic cycle into two categories. The first cycle is power cycle. Second one is refrigeration cycle. Okay, in power cycle, we broadly classified into two types. First one is vapor cycles, second one is gas cycles. In the same manner, refrigeration cycle broadly classified into two categories. First one is vapor cycle, second is gas cycle. Okay, what is meant by power cycle? Power cycle means these are the work producing device. Let us say work producing device means turbine. In the refrigeration cycle, these are the work absorbing device like refrigerator. Okay, for the example, vapor power cycle, Rankine cycle is the example for the vapor power cycle. Okay, next for the example, gas power cycle is Brayton cycle and our air standard cycles like Otto cycle, diesel cycle. And in refrigeration cycle, vapor cycle, the example is VCRS, that is vapor compression refrigeration cycle. And for the gas cycle, example is Bell-Coleman cycle. Okay, this is the broad picture of total thermodynamic cycle. Okay, in this class, we learn detail about the vapor power cycle. Let's start the vapor power cycle. Before going to the vapor power cycle, we should learn about how that power plant works. The power plant starts with the pump. Okay, the function of pump is to increase the pressure of working substance and pump it to the boiler. What is the function of boiler? The boiler function is to increase the heat addition, or in boiler we supply the heat. Okay, and that whatever the pumped water is, it will convert into the water vapor, that is the steam. Okay, that steam is expanded into the turbine. Okay, next, after that we produce the work in the turbine, it will recycle to the condenser. In condenser we reject the heat. Okay, in condenser we reject the heat and we remove all heat from the water and we send back to the again into the pump. Okay, and next is Carnot vapor power cycle. We will learn the Carnot vapor power cycle through TS diagram. Which diagram? TS diagram. Let us change the color. Okay, first we have to start the vapor dome. This is called vapor dome. In this vapor dome, this portion is saturated liquid and this portion is vapor line. Okay, whatever the steam water vapor is present here, this is the saturated liquid. Okay, here dry. Let us change color by white. Okay, in Carnot vapor power cycle, heat addition is done by constant temperature. This is the process 2 to 3. Heat addition is constant temperature. Okay, and the process 1 to 2 is the pump work. Process 1 to 2 is a pump work which is done by isentropically. Okay, the process 3 to 4 is isentropic expansion, that is the turbine. And the process 4 to 1 is condenser. Okay, I will repeat again. You will use another color. Okay, process 2 to 3 is heat supplied. Process 1 to 4 is heat rejected in condenser. Okay, process 3 to 4 is turbine work. Here the process 1 to 2 is pump work. Okay, this is the boiler pressure, which is PB. Sometimes we will denote as pH, means higher pressure. This is the condenser pressure. These all points are we used in to solve the problems. Okay, let us derive the efficiency equation. Okay, what is the formula for efficiency? Efficiency of Carnot cycle is denoted by work done or net work divided by heat supplied, or 1 minus T lower by T higher, means lower temperature, which is condenser temperature. This is the boiler temperature. Okay. Okay, what is the formula for Qin? For Qin means heat supplied. For heat supplied, where is the heat supplied? The portion 2 to 3. See guys, 2 to 3. So heat supplied formula is H3 minus H2. Okay, H3 is Hg at higher pressure and H2 is HF at higher pressure. Why? See here, this point 3 is a dry saturated line, so that's why this is the Hg. This is 2 is a saturated water line. Okay, means saturated liquid line, that's why HF. Okay, next, the next formula is work done. What is the formula for work done? Okay, work done is equal to efficiency of Carnot cycle into heat supplied. What is the efficiency? 1 minus TL by TH into what is the heat supplied? H3 minus H2. Okay, this is the formula for heat supplied. This is the formula for work done. If we divide work divided by heat supplied, we will get Carnot cycle efficiency. Okay, moving to the next concept. What is the main drawback of this Carnot vapor power cycle? Listen guys carefully. Okay, what is the main drawback is it is difficult to design a device which increase the pressure of mixture, that is liquid plus vapor. Listen guys, this is the pump work. We can't pump the liquid and vapor. Why? It will form the scale or it will rust the blades, and it is very difficult to pump the vapor. We can pump the liquid, pure liquid we can pump, but we can't pump the steam, what that is water vapor. So that it is difficult to pump the water vapor. This is the main drawback of Carnot vapor cycle. Remember, this question might be asked in MCQ. Okay, moving on to the next slide. Okay, this is all about the Carnot cycle. Okay, so the next cycle is Rankine cycle. Okay, let's change the color of pen. We'll take white one. Okay, through the TS and PV diagram, we analyze the simple Rankine cycle. The Rankine cycle begin with the pump work, that is 1 to 2, and further 2 to 3 is constant pressure heat addition. In Carnot cycle, constant temperature heat addition, but in Rankine cycle, constant pressure heat addition. Okay, and that further 3 to 4 is turbine work or expansion in turbine in isentropic. Okay, this is 4 to 1, this is the condenser work. condenser. This is heat rejection, QR. This is the heat addition in supplied or in boiler. This is the turbine work. This is the pump work. Okay. Next, this is the PV diagram. Constant pressure means 2 to 3. Let's go like this. And isentropic expansion. Again, constant pressure heat reduction and constant volume pump work. Okay, this is the process 1 to 2, 2 to 3, 3 to 4. Okay, you have to remember pump work is constant volume and adiabatic. U is 0. This is all about the pump work. You have to remember this. Next, the process 1 to 2 is reversible adiabatic, increase in pressure in the pump in volume, keeping volume as constant. This is the process 1 to 2. This is the process 1 to 2. Adiabatic, increase in pressure. Next, process 2 to 3 is boiler, means heat supplied. Next, so the next process is 3 to 4, that is reversible adiabatic expansion in turbine. Next, the process is 4 to 1, constant pressure heat rejection in condenser. This is all about theoretical part of the Rankine cycle. Let us start the analysis of Rankine cycle to solve the numerical. This is the main part of the Rankine cycle. Please be attentive for the 5 to 10 minutes. Okay, this is the pump work. Process 1 to 2, this is the pump work. See, that is H1. H1 is HF at condenser pressure or lower pressure. Okay, what is the H2? H2 is H1 plus pump work. Okay, what is the pump work? The formula for pump work is VF boiler pressure minus condenser pressure. Okay, PB means pH higher pressure or boiler pressure. P condenser means lower pressure. Okay, this is the formula for H1. H1 is HF because this is the saturated liquid. Okay, H2 is H1 plus pump work. What is the formula for pump work? VF into PB minus PC. You have to take VF at lower or condenser pressure. Okay, the next formula is 2 to 3. We know H1, we know H2. Now we have to find out the H3. The formula for H3 is H3 is equal to H sup, means enthalpy of superheated steam at higher pressure. If in the question they have given superheated temperature, you have to take directly H sup at these two conditions through steam table. Otherwise, one formula is there for H3. H3 is Hg plus CPV, means specific heat of vapor, into T3 minus T saturation. This saturation you have to take at higher pressure or boiler pressure. Okay, Hg also boiler pressure or higher pressure. This is given in the question. So the formula for, we can find out the H3 by two ways. Remember, if in the question they have given superheated temperature, you have to take direct from the steam table. For H3, if they are not given T superheated, then you have to find out by this conventional formula, which is Hg plus CPV, means specific heat of vapor, T3 minus T saturation. Okay, the next is expansion in turbine. See, we know the H3. Now we have to find out the H4. For the H4, we have to know the what is the condition of turbine exit? Okay, that is x4. For x4, this is the isentropic expansion. That's why S3 is equal to S4. What is the condition of the steam at the turbine exit? That is the x4 you have to find out. So the hint is S3 is equal to S4. So S3 we can take directly from the steam table. That is the entropy of superheated steam at higher pressure and superheated tea soup. Okay, now we know the S3 value. Okay, now we know the S3 value. Wait, I will rub this. Note down this. We know the S3. Now we know the S3. From this S3 is equal to SF4 plus X4 SG4 minus SF4. 4 means all these 4 means the condition at lower pressure. Remember, all these condition at lower pressure. This is the higher pressure. Now you know the S3, you know the S4, SG4, S4. From all this you have to take from steam table. The unknown is X4. You have to find out the X4. That is the condition of the steam, whether it is a wet steam, superheated steam, whatever it is. You have to find out the X4. Once you find the X4, your next work is once you find the X4, you have to find the H4. That is the HF4 plus H4 HG4 minus HF4. Okay, this X4 value you have to put in this, and this is the all these enthalpy values you have to take from P lower, that is the condenser pressure. Okay, now you know the all enthalpy values. Okay, the formula for heat rejection now is H4 minus H1. The net work is turbine work minus pump work. Okay, the efficiency formula is work net divided by heat supplied. Okay, what is the formula for work net? Turbine work minus pump work. What is the formula for turbine work? H3 minus H4. Turbine work H2 minus H1. What is the formula for heat supplied? H3 minus H2. This is done in boiler. Okay, now we have to write Q net. Turbine work minus pump work means H3 minus H4 minus H2 minus H1 divided by Q supplied. What is the Q supplied? Means heat supplied, H3 minus H2. This is all about the efficiency. In problem, you have to find efficiency. Remember, this is all about the analysis of Rankine cycle. Okay, first pump work. How you find out the pump work? H1 is HF at lower pressure. H2 is H1 plus pump work. For pump work, VF and PB minus PC. Next, 2 to 3 constant pressure heat addition in boiler H3, and you have to find out from Hg plus CPV T3 minus Tsat. Next, turbine work is you have to in turbine work we have to divide the work, like you have to first find out the X4, that is the condition of the steam at turbine exit. Next, H4, from that X4 you have to find out the enthalpy at turbine exit, that is the H4. H4 is X4 Hg4 minus HF4. Okay. Okay. The next concept is energy balance in condenser. So what is meant by energy balance in condenser? Heat lost by steam, that is equal to heat gain by cooling water. Whatever the loss of heat to the steam, it will gain by the heat by cooling water. Okay, let us write the equation. Heat loss by hot steam, heat loss by hot steam is equal to heat gain by cooling water. What is the formula for heat loss by hot steam? Mass of steam H4 minus H1. What is the heat gain by cooling water? Mass of water Cp of water into T2 minus T1. This is the rise in temperature. In the question sometime they have asked like this: find out the rise in temperature in the condenser. You have to find T2 minus T1. The value of this is 4.18, so specific heat of water. Okay, this is the mass of water, this is the mass of steam, this is the enthalpy of turbine exit, this is which means entry of condenser, this is the exit of condenser, this is the direction. Okay, this is all about the energy balance in condenser. Why this need energy balance in condenser is in some problems they have given like this: find the rise in temperature in condenser, or they have given all these content, and sometime you have to find out the mass of the steam. Whatever the unknown is, we have to find out in condenser. Okay, after this, the next concept is the work ratio. This is the very important concept. In some problem they have to ask work ratio, find the work ratio. The formula for work ratio is net work, that is a turbine work minus pump work divided by turbine work. Okay, net work divided by turbine, that is a positive work. Work ratio tells about the how much of turbine work is consumed by the compressor. Compressor means, or here in Vapour cycle we use the pump. Okay, let us see by the example. Work ratio is 0.96 to 0.98. That means the remaining 0.4 or 0.2, that is taken by pump. Okay, the remaining, whatever the remaining is taken by the pump. For example, if the turbine produce 100%, in that 100%, 4% is taken by the pump. Okay, we will extract that work from the turbine and that work will given to the pump. Okay, this will tell the work ratio. Okay, if in the question we give as 0.96 to 0.98, work ratio means the pump taken by 0.4 to 0.2. Okay, the next concept is back work ratio. What is back work ratio? What is meant by back work ratio? Negative work by turbine work. What is back work ratio? Negative work by turbine work. Let us Okay, this is the formula for back work ratio, pump work divided by turbine work. Some note is there. Okay, what is that note? Work ratio plus back work ratio is always is equal to 1. Okay, note down this is very important. This might be asked in multiple choice question. What is work ratio plus back work ratio is always equal to 1. Okay, moving on to the next concept, that is the specific steam consumption. Means how much steam we require to produce 1 kilowatt power. Okay, specific steam consumption. Okay, specific steam consumption. Mass of flow steam required to produce unit power. Unit means 1 kilowatt or unit power. Okay, to produce 1 kilowatt power, how much mass we require? We can write this mass of steam divided by this dot means we will take with respect to time, mass of steam into network. This is kg per second. This is also kg per second. This is kilojoule per kg. If we cancel this, second kg. Specific steam consumption. Finally, we left with the 1 divided by work net kg per kilojoule. If you multiply hour divided by hour, means this kg per hour, this hour goes down, that is, I will write again, kg per hour divided by kilojoule per hour. Okay, we have to convert this hour into second, that is kg per hour. We have to keep like this only, kg per hour. This is the 1 by 3600. 1 hour is contains 3600 second. So this is kg per second. Left with this 3600 goes upside. So the final formula for, I will write here, specific steam consumption is 3600 divided by W net. The unit is kg per kilowatt hour. You have to mug up this formula. Specific steam consumption, and this is kilojoule per kg. Okay, this is all about the analysis of simple Rankine cycle and Carnot cycle. Write all these formula and note down these formulas which will help you to solve the problems. In next video we will discuss about the problems. We will move on to the problems in next video. Thank you for watching my video. Please like and subscribe my YouTube channel.